So welcome everyone to the spectral geometry and the clouds. Today is a special session because it's been the 100 talks today. Semyon has the honor, or perhaps we have the honor rather, to have him give a talk for this special number in base 10. And so we have the pleasure of having Semyon Dyatlov from MIT today, who will speak about Ruelle zeta function at 0 for nearly hyperbolic 3 manifolds. And the floor is yours, Semyon.
Thank you very much, Alexandra. It's a great pleasure to be giving the 100th talk, and thank you very much for inviting me. So today, as I mentioned to Laura, I was incredibly lucky that the other two projects I've been working on has already been spoken about here by my two co-authors. So today I'll present to you a somewhat different or alien kind of spectral problem for most of you, which is one that comes from hyperbolic dynamics. So I'll speak about the order of vanishing of the Ruelle zeta function for the geodesic flow on a negatively curved free manifold. So I'll have a negatively curved manifold, and I'll define what a Ruelle zeta function is in a couple slides. It's some kind of function that's constructed using the lengths of closed geodesics on this manifold. And then I'll be studying the vanishing order at 0 of this Ruelle zeta function. Why? Well, there is a long history of study of this, which I'll also explain later, but generally we think that the zeta function value at 0, or the order of vanishing at 0, so the singularity at 0, has to do something with the topology of the underlying manifold, which is pretty cool, that you have this dynamical quantity, and then from there, you can see a relation to a topological quantity. So in particular, if my metric is hyperbolic, so if it's constant negative curvature, then it was shown back in the 80s by Fried that the order of vanishing of the Ruelle zeta function is given by 4 minus twice the first Betti number, which is the dimension of the Ram cohomology on 1/4. So here's a very neat formula in constant curvature. And the question is, what's going to happen in variable curvature? And so in variable curvature, so this is the work that I'll be presenting today. It's joined with Mikhailo Tsekic, Ben Kuster, actually Ben Delarue. I'm sorry, Ben, I forgot to reflect your name change in my talk slides. And Gabriel Paternan, back, well, now 2 years ago. What we show is that for a generic perturbation of a hyperbolic metric, the order of vanishing changes to 4 minus once the Betti number. Now, is this surprising or not? I don't know, but to me personally, it was surprising, because if we, instead of studying free manifolds, study surfaces, then in older joint work with Zworsky, we showed that in this case, the order of vanishing of the zeta function at 0 is always equal to the Betti number, so twice the genus, minus 2, regardless of whether you're constant curvature or variable curvature. So in dimension 2, so for surfaces, for geodesic flows in negatively curved surfaces, this order of vanishing is a topologically determined quantity. So for a while, Zworsky and I thought that this is going to be like that, maybe in all dimensions. Not that we had a proof, and for a good reason, because it turns out that already in dimension 3, the situation is very different. So a perturbation changes this quantity to something that's still topologically determined, but it's a generic perturbation. So this means that the order of vanishing really depends on things beyond just the topological information. And the motivation comes from something called Fried's conjecture that relates the values at 0 to analytic torsion, and that's I'll mention that at least briefly later, even though our result doesn't say anything about the value or about torsion, but it's important motivation. All right, so here's the setting now. Let me talk a little bit about the setup we have here. So there will be a spectral problem, but it's not immediate where it comes from. So it'll be some time before we get to the spectral side of it. So let's consider, for now, let's just do the case of any dimension. I'm going to consider sigma, a compact, connected, oriented, for simplicity, Riemannian manifold of dimension m. Then the geodesic flow is not a flow in sigma, it's a flow in the sphere bundle. Right? Because you need to know the position and also the direction of velocity to know where your geodesic ends up. So I'm going to call the sphere bundle as M. So most of the analysis will be done on M, and will most of the time be forgetting that it's actually equal to a sigma. And then this geodesic flow is actually a contact flow. So you can define a canonical contact one form on the sphere bundle. It's done here. It's the only one form you could define, basically, if you have just the Riemannian metric. And then, well, it's a contact form. And then the geodesic flow is the generator of the geodesic flow, which I call X, is the Reed vector field of this contact form. So it satisfies those two identities that I'm highlighting here. I think when I move my cursor, you should be able to see where it is. Right? So you have a contact structure for the geodesic flow, and that's something that we will be using. We'll be using this contact form and this kind of duality between the contact form and X. All right. Well, it's well known, going back to the work of Anosov, that if G has negative sectional curvature, then the geodesic flow has the Anosov property, even though Anosov, I think, called it the S property. I think his main result was that every U system is also an S system. That's the statement of the theorem. But anyway, in modern terms, we call it Anosov, or uniformly hyperbolic flow. But this means that the tangent space to M, which remember itself was the sphere bundle, decomposes into three pieces, three sub-bundles: the flow direction, E0, the unstable direction, the stable direction. And then you have exponentially fast exponentially fast contraction of the differential of the geodesic flow on the stable tangent vectors in the forward time direction, and the unstable ones in the backward time direction. So hyperbolicity of the geodesic flow is also something that we will be using very strongly, and that's why we restrict. Well, our theorem is much more restricted than that, but generally in this analysis we restrict negative curvature or at least things that have this property. All right. So for later use, since I'm going to be using microlocal analysis, and microlocal analysis is better done on the cotangent bundle than the tangent bundle, I'm going to define these dual stable and unstable sub-bundles of the cotangent bundle to M. And again, M is a sigma, but don't think about sigma. Just think you have this flow on M, which was the geodesic flow on sigma, and then we're just looking at its tangent spaces and cotangent spaces. Let's not worry about how those relate to the geometry of sigma yet. All right, so here are my dual ones, and the order is switched, which makes things convenient later. All right, so those will come up again, and so those are sub-bundles of the cotangent bundle to M. All right, well, okay, here's the object that we study. So the object is actually very easy to write down, which I think is very appealing. So here's the real zeta function, which is an infinite product. It's an Euler type product over the length of all primitive closed geodesics. So primitive means it's not a positive, it's not a multiple of a shorter geodesic. So here's this product. It features lengths of closed geodesics, these T gammas, and then you have the complex variable lambda, and this converges when real part of lambda is sufficiently large because the number of closed geodesics grows with most exponential. So what's known about the zeta function is that it actually continues meromorphically to the entire complex plane. Once you write a zeta function, it's a usual thing that you want something that's, you usually write something as a sum or a product or some formula that only makes sense usually in a half plane. Like think about the Euler product for the Riemann zeta function, right? And then you try to continue it to the entire complex plane, and then hopefully you get some zeros or poles or something, and that those singularities might tell you something about the original sequence. Now, here we're going to be going pretty deep into the continued region, so we're not going to be able to extract, asymptotics of the geodesics from this. But anyway, so what's known is that it continues meromorphically. That was proved by Giulietta, Leverani, and Polycott. And then Dvorsky and I later produced a different proof, which is the proof that we'll be using in this gives a bit more microlocal information that will be useful for us, certainly. And it's been a long study of this meromorphic continuation. So it was first conjectured in a related setting by Smale in '67. All right, and then as I said, I'll study the vanishing order of that at 0. So it's a meromorphic function, and then you can define the vanishing order. That's just an integer, right? So I'll really be only interested in lambda equals to 0, near lambda equals to 0 in this. All right, and so the question, as I said before, is can we describe this vanishing order in terms of some topological invariants, for example, in terms of the Betti numbers? So the Betti numbers of sigma, but the Betti numbers of M, the sphere bundle, are related to the Betti numbers of sigma by a well-known construction of the Giesian exact sequence. All right. All right, so what's known about those? So people have studied those for a long time because, well, those are fascinating objects to study. And one thing I should say, even though we do not do it in our paper, but in a lot of previous work, it comes in handy. You can actually look at more general zeta functions. You can twist by a representation, or this corresponds to taking a bundle with a flat unitary connection. Okay, and the trivial representation would correspond to the old zeta function. Now, this twisting helps because you can choose a representation so that the de Rham complex is acyclic. So the corresponding de Rham cohomology classes that are defined using this representation are 0. Since I'm not going to be using a representation, I'm not going to get into details of how this works here. But then maybe the earliest, one of the earliest works on the understanding of singularity of the Ruelle zeta function 0 was in the hyperbolic case. So that was done by Fried in the paper already mentioned. In particular, in dimension 2 and 3, he computed, I mean, he did it in all dimensions, but here's the results in dimension 2 and 3, how you compute the order of vanishing. Now, if rho is acyclic, so if you have an acyclic representation, and this 2 and 4 are actually 0, because this 2 and 4 should really be the 0th Betti number. And so you get a function, which is this Ruelle zeta function is holomorphic at 0 and non-vanishing. And then, of course, once you have a holomorphic non-vanishing function where you somehow proved that its order of vanishing is 0 at 0, well, it's irresistible to try to understand the value, right? That's the next thing you would try to understand. And Fried did that, and he described it in terms of the analytic torsion, which is the same as the Reidemeister torsion, which is a kind of next level topological invariant associated to sigma and rho. And then he conjectured that the same formula for the torsion holds in a more general setting of locally homogeneous spaces, and which these are manifolds which still have a lot of symmetries. And so it was proved, this conjecture was proved in a setting of locally symmetric spaces, which are, again, spaces with a lot of symmetries. They always have a transitive action of a Lie group in particular, among other things. But there is still plenty of them beyond just hyperbolic spaces. So that was done by Shen following earlier work. Now, all of the above was in this locally symmetric class, where you can use Selberg trace formulas and representation theory. You have a lot of explicit formulas relating various quantities. And you can decompose, you can think of your, not the sphere bundle, but the frame bundle is a quotient of a Lie group on G mod gamma. You can decompose L2 of that by irreducible representations of G and so on. So you can really do a lot of what I would consider more algebraic work here, this compared to what we do. So doing this, you can prove those very nice results. Now, all right, so what I'm going to be talking about is mostly what happens in the non-locally symmetric case. So there you lose this access to the algebraic tools. What was known is that, well, there was this result with Zworsky that I already mentioned. So for surfaces, we know what happens, what the vanishing order is. And actually applies in general contact and also flows in dimension 3. Then there was some extensions by Hatfield and Borns, Ruelle and Shen. And there was a study of volume preserving anossel flows which are not contact. So it's kind of an hierarchy of what kind of anossel flow you could have. And then, so that was done by Tsekich and Paternano, and they showed that there is sometimes things don't just depend on the topology, but also depend on the kind of on certain properties of the flow. Now here's a nice result by Dan, Guillermo, Riviere, and Shen. So they proved Fried's conjecture. So they conjecture about the value of the zeta function, how it relates to the analytic torsion for any nearly hyperbolic 3 manifold. It's a special case, of course, but it's very nice. It's the first result like that in a case which is not locally symmetric. And there are a few more related works which are a little bit harder to describe the results without introducing a bit more. So I'll just list it. All right, well, so here's our result as advertised before. So we are going to consider now, we're going to consider 3 manifolds. More specifically, we're going to take a hyperbolic 3 manifold, sigma, and GH is the hyperbolic metric. And then we have 2 results. The first one is that the order of vanishing of the Ruelle zeta function at 0 for the hyperbolic metric is given by 4 minus twice the first Betti number. The second result is that for a generic conformal perturbation of this GH, so if you take a metric that's a generic conformal perturbation of the hyperbolic metric, then the order of vanishing is 4 minus 1 the Betti number. Here I explain explicitly what I mean by generic conformal perturbation. So this is an open dense set of perturbations that you can attend. We could probably study also general metric perturbations, but it would just be more technically complicated in some places, and I don't think we'll get a different answer by studying general metric perturbations. So we're stuck to the conformal ones, which are easier for the writing. So yeah, this is the first result on instability of the Ruelle zeta functions under of the order of vanishing at 0 under metric perturbation. So here it really gives you a fairly large class of manifolds for which the answer in variable curvature is different than the answer in constant curvature. And so it just tells you that, well, the situation becomes much more complicated. So we don't have a clear understanding of all metrics, and probably never will, but maybe we can understand generic metrics. But in this case, again, the answer would be different than what it is in the constant curvature case. Now, part 1 is this old result of Fried, but our proof is different, and we use, we reprove Fried's result using microlocal and geometric techniques, which make it possible for us to carry out part 2. Right? Well, okay, so there is finally we're getting to so there was a it's a spectral geometry seminar, right? So there's been quite a bit of geometry, I want to think, and there's been even more dynamics so far in the talk, and now we're going to talk about the spectrum. So what's the spectral? What do spectral problems have to do with this? Well, the general idea is that you want to write this dynamical zeta function as a characteristic polynomial of a certain operator. By analogy with matrices, then the order of vanishing at 0 would correspond to dimension of generalized eigenspace, and you can try to study the eigen or generalized eigenvalues of your matrix to understand the order of vanishing. And that's basically what we do. Except we don't have a matrix here, we have an operator. And I'll define what the operator is, but it's a pretty big operator in the sense that if you try to define this determinant literally by some kind of infinite product, it is not going to converge ever. Well, of course, it already, this doesn't even make sense for 0, right? If you take determinant of lambda times the identity and it's an infinite dimensional space, it just doesn't make sense. So the way it should be understood is that the log derivative of that should be the trace of the resolvent. And that resolvent is still not trace class, so one needs the right definition of trace, a so-called flat trace. That is a microlocally informed definition of trace that will make it possible to define this expression and meromorphically continue. Well, then one expects that the vanishing order 0, as I said before, should be the space of generalized eigenstates of this operator at 0. For the real zeta function, the situation is a little bit more complicated because instead of a determinant, I think in supersymmetry they would call it a super determinant, which just means it's an alternating product of determinants. So the vanishing order of the real zeta function, you don't just have one operator, but you have finitely many operators corresponding to different degrees of differential forms, and you have to combine these dimensions with both alternating signs together. But ultimately, it reduces to understanding those spaces of generalized resonant forms that I will describe a bit later. And then the strategy is to understand those spaces in terms of the de Rham cohomology, and that's how you relate it to topological information. So in this talk, I'll mostly focus on the case of one forms. The case of zero forms is in a way trivial, and then the case of one forms is the first interesting case. I'll only talk about two forms a little bit. All right. So, okay, well, now some specifics. So that was general strategy. Now, how do we, how does it actually work? So remember, my M is going to be the sphere bundle of a 3 manifold. So that's going to be a 5-dimensional manifold, M, right? And then X is the generator of the geodesic flow. So it's a vector field on M which generates geodesic flow. So the flow of that is the geodesic. Now, the operators that we study, the operators are very simple, very natural geometric operators. They're just the Lie derivative with respect to the geodesic flow, so Lie derivative with respect to X, acting on differential K-forms. The only twist in the story here is that you don't study all differential K-forms. It turns out what you should study is K-forms which are annihilated by X, so so-called perpendicular K-forms. So that's a very, very natural operator. The more difficult part in understanding what these resonant spaces are that we need to, or generalized eigenspaces are that we need to compute in order to get our vanishing order, comes in the fact that what's the domain of this operator? So it turns out that even if you consider, maybe I'll take a small detour, again, since this is a spectral geometry seminar. If you consider just the operator X as a differentiation along the geodesic flow, so this corresponds to zero forms. So it's a first order partial differential operator. You can see it's going to be essentially self-adjoint on L2. On a compact manifold, any first order symmetric operator is essentially self-adjoint. But the spectrum of this operator X on L2 is going to be continuous, except for one eigenvalue at 0, the constant function. Everything else is continuous. It's continuous spectrum. So you don't expect any kind of discrete spectral information coming out from it. But what it turns out that we're not using the correct space to study this operator. We're not using the correct domain in a way. So instead of using L2, we should study some kind of distributional space. Now, if you look at a problem like XU equals F, so the derivative along a geodesic flow of a function U is equal to F, then if you're not doing things in L2, you could think, okay, maybe we should take U to be smooth and F to be smooth. This turns out to be too restrictive. You're not going to get a Fredholm operator this way because you're not going to have existence. You need a lot more conditions on the right-hand side for it to be the derivative along a geodesic flow of a smooth function. You need the right-hand side to integrate to 0 along each closed geodesic. You see, infinity is not the space we need. Well, you could consider the space of distributions. Maybe U should be a distribution. We're solving XU equals F, where F is a distribution. Well, that's not the right space for the opposite reason, because the kernel is too big. Because if you take any closed geodesic, then the delta function on a closed geodesic is a distribution which is killed by the generator of the geodesic flow. It's invariant under the geodesic flow. So it turns out that, however, you can define just the right kind of space using the fact that the flow is hyperbolic, called anisotropic Sobolev spaces. I'm not going to get into the details of how these work, but with these spaces, you can make the resolvent family of the operator to be a Fredholm operator of index 0. So you can really study it. It's like an operator with discrete spectrum. Effectively, it's these spaces, the operator will no longer be symmetric, so it's not a self-adjoint spectral problem, but you will have a spectral problem with discrete spectrum here, right? And so that's the kind of spectral problem that we generally consider in this setting. Yeah, so there is a very long list of references, and this this has been around for some time, and we'll use the microlocal approach to those spaces, which originates in the works of Ford, Shostrom, and Shostrom. Now that we have this resolvent family, which is Fredholm, so then we take its inverse, you're going to get a Fredholm, you're going to get a meromorphic family of operators with poles of finite rank. And so that's what that's a kind of spectral I'll study. And then the poles of this resolvent are the polyquaternion resonances. Remember, we were trying to take the trace of this, and that was the log derivative of our zeta function. All right. Well, if we look at those, so what are the corresponding eigenstates? These are the so-called generalized resonance states. They are written here, which is the usual definition of a generalized eigenstate, except you need your U. Now your U is a current, so it's a distributional valued differential K form on my manifold M. And well, you need some power of the Lie derivative to kill that, and it has to be in the domain of the operator, which I'll specify a little bit more later. And so what we did with Dvorsky is we showed that we basically executed the strategy that I described before with a characteristic polynomial formally strategy, and showed that the order of vanishing of the Ruelle zeta function at 0 is an alternating sum of the dimensions of these spaces of generalized resonance states. Right? So that's, again, kind of by analogy with how the order of vanishing of a characteristic polynomial of a matrix at some point is equal to the dimension of the space of generalized eigenstates at this point. This spectrum. Oh, sorry. And so this result, it's ultimately it's just an identity, right? But we the proof uses a fair amount of analysis that I'll almost entirely sweep under the rug here. It uses propagation of singularities due to Hormander. It uses radial estimates going back to Melrose's work in the 90s, and it uses the Atiyah-Bode-Gilliland trace formula to relate closed geodesics to the flat trace of the resolvent. So this trace formula is how the closed geodesics, which were used in the definition of the zeta function, finally entered it. All right. So now that we know how to express this order of vanishing at 0 in terms of the dimensions of these still quite mysterious spaces, at least you will believe me that the theorem that I presented before follows from this more detailed description of the dimension of the spaces, which we put. So here is a table of the dimensions of the spaces of forms. So, my manifold M is 5-dimensional, but I'm looking at perpendicular K forms. So they have to be killed by the generator of the geodesic flow. And so this means that the non-trivial cases are 0, 1, 2, 3, and 4 forms. And so here's the dimension of these resonance spaces for a hyperbolic case and for generic conformal perturbation case. And if you take the alternating sum, then you see you get the numbers that we get before. But it's much easier to market the dynamical zeta function because it's something that you can define very simply. And then this order of vanishing is something that, again, you can define simply rather than getting into what these spaces are. But really what we're after is we're trying to compute a detailed structure of these spaces. And there is a certain symmetry here. You can see that the K and 4 minus KKs are going to be the same. So really, we only need to study forms in dimension 0, 1, and 2. This is something much simpler than concurrential, which is just an explicit isomorphism. All right. So we compute these dimensions, and that's how we get the order of vanishing of the zeta function. Now, how do we do this? All right. So that's where it gets a little bit thick, because I have to describe to you at least a little bit, well, what are these generalized resonance states? I mean, one part we know, they should be currents, and they should be killed by some power of the Lie derivative. But the problem is what's the domain of the operator? So what kind of regularity assumptions do we need to put on those? And it turns out that if you don't study the Fredholm problem in itself, if you just study the eigenstate, so to speak, then there is a cleaner way to formulate it, and that is the wavefront set of the corresponding current should be in the dual unstable, should be contained in this dual unstable bundle, which I introduced some time ago. Now, this only leaves one question: what's a wavefront set? And that's a question that I'm not going to answer here. in detail, but you can think of it as the wavefront set is a generalization of singular support. So singular support of a distribution tells you at which points it is not locally C infinity. But if you think about it, for a function to be C infinity and say compactly supported is the same as the Fourier transform rapidly decaying. But what if I only ask my Fourier transform to be rapidly decaying in some directions when I go to infinity and not others? Well, if I combine this with the notion of singular support, which has spatial localization, so I get this kind of both spatial localization and Fourier localization, I get something called the wavefront set. It takes some work to understand that the subject actually makes sense, which I'm not going to do here. Luckily, it was done by Hormander for us some 50 years ago now, 60 years ago. And it's a standard objective study in microlocal analysis. And so this wavefront set tells you, if the wavefront set is empty, this means that your U is smooth. And a wavefront set is always a conic closed subset of the cotangent bundle without the zero section. Well, our requirement turns out to be that the wavefront set of U is contained in this dual unstable bundle, which is something that's it's defined using the hyperbolicity of the flow. So you can see that, and when you see what pops out, you can see that this really only makes sense when the flow is hyperbolic. And what is more is that we fix a time direction here, because if you reverse the direction of the flow, stable and unstable change. But that's the one that we study. The reverse time direction corresponds to the adjoint operator, but you have to make a choice. All right, so this turns out to be this wavefront set condition. Turns out to be just the right kind of condition for the equation xu equals f, so the derivative of u along the geodesic flow is equal to f, to have a unique solution, modulo a finite dimensional space. So that turns out to be the correct condition. Oh, sorry, wait,
sorry.
Yes?
I just wanted to let you know you have a question in the chat.
Oh, yes, I hid everything. Let me see, how do I, there's already a question.
I can read it out to you.
Well, it's good that people are listening. Yes, I'm reading. It's the unstable.
Okay, good.
Yeah, that's right. EU star. Okay, the question is EU star related to U? No. So here U is just a function U, and EU star is U for unstable. EU star is fixed. It's the, where am I? I introduced it along. There you go. It's at the bottom here. There's not too many letters in the English alphabet, so in the Latin alphabet. Yeah. So it's defined using the stable unstable decomposition. All right. Where was I in this whole thing? Okay. All right. So that's the spaces that we need to study. And of course, it's not very satisfactory to you because you don't know necessarily what a wavefront set is. But those spaces are nice because in particular, they're closed under the differential operators. So wavefront set is not enlarged by applying a differential operator to your U. And a lot of the things we're doing actually in this paper is we're relying on the analysis built somewhere else and doing kind of algebra, really the differential geometric computations. And those spaces are very nice because you can do a lot of natural operations with C infinity. You can do those operations also with these spaces. All right, well, okay, so now we need to understand this generalized resonance states. Now, how do we do it? If you're teaching a linear algebra course and you have you need your students to compute the Jordan normal form. How are they going to do it? Let's say your matrix is already nilpotent, so you just have this here. Well, right. So how do you do it? Let's not assume our matrix is nilpotent, but instead, if you want to understand the generalized eigenspace of a matrix, you usually start by understanding the eigenspace, right? So you first solve the equation PU equals 0. And then after you solve that, how do you solve P square U equals 0? Well, if P square U equals 0, then PU is in the first space, right? And then you can continue from there. So here we'll also start with the space of resonance states. You see, the spectral problem is not self-adjoint here. And so in some situations, we do actually get generalized resonance states. So we do have to respect this difference. I should also say, for those of you who like Hodge theory, there's a kind of funny formal analogy. you know, the Hodge Laplacian is d delta plus del d, right? And d square and del square are both above 0. Now, this Lx, the Lie derivative by Cartan's magic formula is dIx plus Ixd. So, and formally, Ix plays the role of del in some of the algebraic manipulations. However, when you do Hodge theory, at least on a compact manifold, one of the first things you show is that if the Laplacian u is equal to 0, then both du and del u are equal to 0. And that's done by integration by parts and using the fact that del is d star. There is nothing like that here. So you can't be in the kernel of this thing and not be closed, or not be in the kernel of Ix. So we have to be careful. I mean, here we're already considering things which are in the kernel of Ix because we're in this perpendicular bundle, but those resonance states, they do not have to be closed. So the quote unquote Hodge theory here would be much more complicated than the compact Riemannian case. All right, well, for later use, there's also co-resonance states. Again, the problem is not self-adjoint. So those are elements in the kernel of the adjoint of the operator. And the domain changes to ES star when you look at the adjoint, it turns out. And there is a natural identification of those with resonance states because the geodesic flow is time reversible. And then you can pair resonance states and co-resonance states. So you cannot multiply distributions in general, but you can compute an inner product of resonance state and co-resonance state because the wave functions don't intersect. So that's something that we will also. It's very analogous to matrices, you know. When you're studying matrices, you naturally want to pair elements in the kernel of a matrix with elements in the kernel of the adjoint. All right, and in particular, you can see that this pairing between resonance states and co-resonance states, if this pairing is non-degenerate, that's equivalent to semi-simplicity, which means that there are no Jordan blocks. So all generalized resonance states are just resonance states. You know, it's a nice way to check there are no Jordan blocks. So for a matrix P, there are no Jordan blocks at 0 is the same as saying that the kernel of P is transversal to its range, right? And that's the same as saying by, you know, identifying the range by duality. It's the same as saying if you take elements in the kernel of P and kernel of P star, the pairing on those elements as you know, vectors and covectors is non-degenerate. That makes it possible sometimes to establish semi-simplicity by computing this pairing and showing that it's non-degenerate. All right. Well, as I said, I'll focus on case k equals 1, so 1 forms. One of the reasons is because the case k equals 0 is turns out to be simple, or you using standard tools in this business, you can show that the resonant states, generalized or not, is just there's only one, the constant function. And there's nothing else interesting there, right? So in particular, the dimension is 1. So now I'm going to try to explain to you a little bit what's happening. I'm not necessarily going to explain how we do it. Half of it is explicit computation, which is, you know, can be repeated, and how to describe the spaces of generalized resonance states in the hyperbolic case. So, well, okay, I'm not getting to the hyperbolic case yet. Okay, so there is a little bit more of general theory we can do here before we get to perturbations of hyperbolic spaces, and that's we can study resonant 1 forms. So Lx kills you and you are in this space, which are also, so this becomes really like manipulations and differential geometry. So let's look at the resonance states which are closed. You see, when you write this condition to be a resonant state, it's the same as saying Ixu is 0. That's something we imposed in the bundle, and Ixdu is 0. That's what it means for Lxu to be 0 by Cartan's magic formula. So okay, so let's study the closed one. So that's where Ixu is 0 and du is also equal to 0. So kind of in Hodge theory would be like harmonic functions, right? D and del are both 0. Well, what happens is you have a closed 1 form. Okay, it's not a form, it's a current because it's distributional value. But for de Rham cohomology on a compact manifold, it doesn't matter what regularity class you use to define your de Rham cohomology. You can use C infinity, you can use a Sobolev class, you can use distributions. and you're going to get exactly the same cohomology classes. And one of the major reasons is because if you think how Hodge theory is proved, the typical way is to use the elliptic parametrics for the Hodge Laplacian. That's a pseudo differential operator, and that preserves all of those classes. Well, it turns out that this parametrics also preserves our classes with the wavefront set. And so if we define the cohomology theory using those classes, no matter what kind of set I put here in my wavefront set restriction, I'm going to get the same kind of thing. So what I can do is I can take this current and I can look at the cohomology class of that. That's a well-defined thing. But more specifically, if I have any current in D prime U star, and it's closed, or more generally, du is smooth, I can always write it out as decompose it as a smooth closed one form, for which the usual de Rham cohomology class makes sense, plus D of a rough form in the same class. Okay, so it turns out that we have this cohomology map. You can do it on any resonant K forms which are closed, right? Here I didn't use it, it's a one form yet. But it turns out that on one forms, it's an isomorphism. So if you just want to identify closed resonant one forms, they're in one-to-one correspondence with de Rham cohomology classes. The issue, of course, is not all generalized resonant one forms could be resonant one forms, it could be Jordan blocks, and more seriously, in a way, not all resonant one forms are necessarily closed, as we will see. But the closed resonant one forms are in one-to-one correspondence with homology classes by just this projection. And the way you prove it is actually pretty simple. I don't know which, well, once you have the technology coming from those anisotropic spaces and stuff, once you know that this D prime is the right space, let's see, which one should I show? Well, how about surjectivity? So how would you show surjectivity of pi1? Well, you take a smooth one form, which is closed, and you want to say, I want to add D of something to it to make it in this resonance space. Well, it turns out that what you need is, well, so your U, your resonance state is going to be V, or smooth form minus DF for some distribution F, a scalar distribution F. And when you think, well, what does it mean to be a resonance state? Well, DU is automatically 0, and IXU should be 0, which means that you're solving this cohomological equation. XF is IXV. And as I said before, the Fredholm property that we have shows that this equation will have a solution in the correct space. So that's how you do it. Modulo IXV integrating to 0, which is something that's easy to check, right? And there is a similar, well, in even simpler, you can show that this is injected. But we really reduce to the case of functions here, which is why this only really works for one form, so as neatly as it does here. Right. So now, let me tell you a bit about what happens in the hyperbolic case, and then I'll tell you a little bit about what happens for perturbations. And again, I'll focus on one forms. So what we showed is that resonant one forms, which are closed, correspond to de Rham cohomology classes, and the Betti number of M is the same as the Betti number of sigma. That's one. So M is the sphere bundle of sigma. Well, it turns out that in the hyperbolic case, there are more one forms, which are resonant one forms, but they're not closed. And the way you can produce the non-closed ones is effectively by rotating the closed ones by pi/2. Now, you can show that each of those resonant one forms will be a section of a smaller piece of the cotangent bundle to M. And that's a two-dimensional bundle, and it has a 90-degree rotation. And this commutes with the flow in case of constant curvature. Because for constant curvature metrics, the geodesic flow is conformal. So the parallel transport along the flow is going to be a conformal map, or the expansion rate on stable and unstable spaces also is a conformal map. So if you take a stable vector, so a vector in the stable space, and you propagate it along the differential of the geodesic flow, the length is going to be exactly e to the minus t times the length of the original vector, no matter which vector you chose. And so you have this two-dimensional stable space, and you have this conformal map. Well, it's also orientation preserving. Any conformal map, so that's orientation preserving, has to commute with multiplication by 90 degrees in plane geometry. And so that's how we get this extra symmetry, this extra operator, that commutes with the geodesic flow, and it produces more resonant one forms than just the closed ones. And variable curvature is destroyed because in variable curvature, geodesic flow is no longer conformal. Different directions will be, will go to zero, say, along the stable space at different speeds. And so you do not have this symmetry anymore. So yeah, so we get this kind of 90-degree action on resonant one forms, and it turns out that non-trivial closed forms are sent to non-closed forms, and you can actually see that the space of resonant one forms is the direct sum of this. You could probably do it using Selbert trace formula, but we do it in a more geometric way using the geometry of hyperbolic manifolds. All right, and so that tells you why the dimension of the resonant one forms is bigger. So that there is no Jordan blocks here, it turns out, and the dimension is twice the first Betti number because we have these extra things that are not closed. All right, well, we also show a little, we also study what happens for two forms, and it's complicated to describe maybe, but in particular, you actually get Jordan blocks for the hyperbolic case in two forms, which again justifies why we should really think about generalized resonant states rather than just resonant states, because Jordan blocks do appear in the hyperbolic case. All right, so what happens for perturbation? So you see, in the case of hyperbolic metric, we have basically a full description of what happens, as much as is realistically possible. So if you tell me if you tell me what the harmonic forms are on your hyperbolic 3 manifold, I can give you a very precise description of what all the objects that I mentioned before look like. Well, now what we're going to do is we're going to perturb the metric. Now, so our result applies to perturbations only. So as you can guess, we'll probably use some kind of variation of eigenvalue. Okay, so going back to a spectral problem, if you have a matrix A, and so here what happens is our operator, it's the space of resonant one forms is twice as big as we want it to be. Now the closed one forms are not going to go away. We showed that they're always there. We want the non-closed ones to go away. Okay, let's look at a simpler situation. Imagine you have an operator A or a matrix A, and you know that it has a kernel at 0, so it has an eigenvalue at 0. Well, now you want to perturb this eigenvalue, right? So you want to perturb your A and see where the eigenvalue moves. And you hope that it's going to move away from 0. Well, how do you show that a function that's 0 at 0 is not 0 in a neighborhood? Well, really, the only way I know is to compute enough derivatives and show that they're non-zero, right? Sometimes you need to go to second variation, but here we use first variation. So we just perturb our metric and see how do these eigenvalues move, or rather what happens to the non-closed resonant one forms. We want them to move and become resonant states at non-zero values. Well, for that, you need to show that something is non-zero. And what do you need to show? Well, you need to show, let's say for simplicity, my Betti number is 1. So I'm just talking about numbers rather than matrices. You need to show that if you take any resonant one form, which is non-closed, then you pair it with, you take du, so that's non-zero. You pair it with the corresponding co-resonant one form, so that's a 4 form. Then you pair it with alpha, which is the contact form, so it's a 5 form. And then you multiply by the pullback of the conformal factor to the sphere bundle, then you should get something that's non-zero. In general, the derivative of the eigenvalue is the perturbation. The derivative of the perturbation applied to an eigenfunction and paired with the co-eigenfunction, right? And that's this formula. So we want that to be non-zero. If we know that this is non-zero, then we can see that things move away, and then with more work, we can show that this whole picture holds for perturbations. Well, oh, sorry. Yes, there's more question. Yeah, because I should stop at, it's 60 minutes, right?
Yeah, it's 60 minutes, but we
all right, question. You're showing that IU will move off the eigenvalue for closed U, for non-closed U. So it's, I skipped some details. It's a good question, Lor. I skipped some details because, there are some computations there, which are, some of them are more straightforward than others. But so if I have a non-closed, what I want is I take one form, which is non-closed, and I want that to be moved away. So not the closed ones, the non-closed ones. And it turns out that, you compute what's the quantity you need, and you can write it out first in terms of this 90-degree rotation operator and so on, but then it reduces to this expression that features du twice. So that turns out to be the correct expression. After some computation, which we do in the paper, it turns out this is the thing you want to be non-zero. At least you can see if u is closed, then this is automatically zero, right? Because du is zero. And so at least it has the right kind of flavor. And it's quadratic in u. And this j star of du is really the co-eigenstate. J is the operation, right? xv to x minus v. It's the time reversal symmetry for the geodesic. Right? So we need this to be non-zero. Now we have a freedom of choosing a generically. A is my conformal factor perturbation. So that's a smooth function but it's a smooth function on the base. You see, my one form is a form on the sphere bundle, because everything was on the sphere bundle really. But my conformal factor is a perturbation, it's just a function on the base manifold. Just like, if you take a conformal perturbation of the metric, it corresponds to taking a conformal perturbation of the contact form upstairs, but it has to be by a function on the base only. So there's plenty of perturbations of the geodesic flow, which are not geodesic flow of a perturbation of a metric. There are ways, many ways to perturb the geodesic flow as a flow that you're not going to get the geodesic flow of a Riemannian metric. So there's much less freedom here. So you have this three-dimensional space on which A lives, this three-dimensional manifold, and then you pull it up to the five-dimensional manifold, and then you want this integral to be non-zero. So you need to show that this is non-zero for generic A. It's the same as showing it's non-zero for 1A. It's a linear condition as far as A is concerned, right? But in order to do this, you need to show that the push forward of this expression, which features this resonant one form, is going to be non-zero. So that's really what we need to show. We need to show that this distribution is not identically zero. All right. Well, how do you show that something is non-zero? You compute it, right? But there is a little bit of a problem because you're trying to show that a distribution is non-zero. So how would you show that a function is non-zero? Well, okay, one way to do it is to show that the integral of the function is non-zero. Then it's non-zero. Here, you can integrate this form and you get zero. So that is not something that we can do. And even if we could, think about it, the Betti number could be huge. So we would need a certain big matrix to be non-degenerate. We need potentially a lot of freedom and perturbation, depending on how complicated the topology is. And the integral is just one number, right? So, well, another way you could show that a function is non-zero is you can evaluate it at one point and show it's non-zero, right? Now you do not have this possibility for distributions. So this push forward, the expression that I want non-zero for my first variation of this eigenvalue to be non-zero, it's a distribution. So how do you show that a distribution is non-zero? Well, looking at the definition of a distribution, you have to present a test function, so a smooth function, so that the integral against the smooth function is going to be non-zero. But there aren't so many interesting canonical smooth functions on a compact three manifold. And so we have to do something here. And so the difficulty in this part of the paper, I mean, it's not, I'm not trying to say that proving what I'm going to say here is trivial, but my feeling was the difficulty was finding the correct kind of expression that you can compute that makes sense and it's non-zero. And so the expression we found is this. So here's my f. So this is this push forward. It's it's a three form. So I can write really as f times the volume form for some distribution f on the base three manifold. And so what we do is the following. We take the we convolve it as the Koch kernel. So I mean, this operator, it looks ad hoc. There is a reason why it comes up, but you can think about it this way. So if I take any point x on a manifold, okay? Now let me take a big geodesic disk centered at x. Let me integrate my function on that. And here I integrate it with a weight which exponentially decays as you get farther and farther from x. Okay, so that would make sense, and this kind of a geodesic convolution, right? With it. Now, what we do it is, well, we do it on a disk of of infinite size. So we integrate along the geodesics with this weight. If you want, it's a function of the Laplacian. Which function? Well, I don't have a nice formula for this function, but you can write it as an infinite product if you really want. So it's some function of the Laplacian, which is rapidly decaying. In particular, would map distributions to smooth functions. But so this particular expression turns out to work for us for reasons that I'll keep mysterious today. And if you apply it to this distribution, then what you get is the following. So this U, it projects onto a harmonic one form on sigma, or alpha wedge du projects on harmonic one form on sigma, that there is a nice correspondence there in a hyperbolic world. And so let's call this harmonic one form sigma. And then it turns out that this Q for F is some constant times the Laplacian of the length, pointwise length of this harmonic form. So if this F was 0, then Q for F would also be 0. So this Laplacian would be 0. Now here I'm talking about a smooth function. In any case, you would know that you would have a harmonic one form of constant length, and there is a topological argument. I think was known sometime before. That this is not possible. So that's ultimately the quantity that we get to be non-zero. All right, I should really stop. I'll finish with two conjectures. One is that whatever we said happens for generic perturbation, we conjecture it happens for generic manifolds, and you can try to make it work in higher dimensions. Well, you can conjecture anything you want, right? That hasn't been proven false yet. And two is something related to Fritz's conjecture and the value, but all right, thank you for your attention. Sorry for running over. Actually, I didn't. It's exactly one.
No, exactly. Thanks a lot for the presentation today. We have some time for questions now, so if you have them, either unmute yourself or write them.
Oh, okay, very nice, thank you.
Semyon, maybe could I ask what's special about dimension 3 here?
Well, 3 is bigger than 2 and less than 4. So the dimension 2, I mean, if we don't want to get esoteric, dimension 1 doesn't make sense. So the dimension 2 was already done, and the answer was different. What happens in dimension 4 is, I think Dankert, Moore, Riviere, and Shen, they actually computed the dimensions of the generalized resonance spaces, and they found that in the hyperbolic case, it doesn't just depend on the topology, it also depends on certain specific special eigenfunctions, eigenvalues of the Laplacian, which are not 0. So that makes it less hopeful. But anyway, so that's it's conceivable that for a hyperbolic case or general locally symmetric cases, the situation for the hyperbolic or locally symmetric metric itself can be figured out in any dimension. I mean, in a way, people have done it. I don't know if they've done kind of geometrically now that we can plug it in, but the answers become more complicated. You could try to. It would take non-trivial effort to adapt this to the case of higher dimensions.
I see. And you think that your proof in particular would not? There's parts of it which would not carry through.
Well, there is a lot of parts that would not. I mean, the general theory sure applies, but the you don't expect the it's like we analyze one forms, two forms. The analysis would be different because the structure already of one forms would be different. And Kuster and Weiss in their paper actually have a fairly good understanding of resonant one forms there. But well, no, only the closed ones, and then you're just going to get a different answer, as can be witnessed already by this zeta computation of Dankert, Riviere, and Shen that I mentioned. I think it's an interesting project, but it's I mean, in dimension 2, the moral is that everything is very nice, and we did not expect that when we were doing this older work with Zworsky. We thought it would move on. In dimension 3, things are difficult again, and in dimension 4. Well, my guess, the moral will be things are even more difficult.
Thanks, Amir, for the question. Do we have other questions for Semyon? There is one by
chat. Okay, let me open chat.
Yeah.
On slide 3, what's the operator between two norms for estimate? Oh, that's okay. So it's a question about definition of hyperbolic properties. So phi t is a flow, right? Depending on t, and then I want to. So for example, ES is a subbundle, which is invariant under phi t. So ES is a subspace of the tangent space at any point. So here, this is uniform in the point. So I take an arbitrary point in the tangent, in the unit tangent bundle. Let's call it rho. Then I have the tangent space at rho. That's a 5-dimensional space for 3 minimum. Right, and then you get this ES as a 2-dimensional space. So you take this differential of phi t, and it will map the stable space at rho to the stable space at phi t of rho. And I want the norm of that to decay. Because of the constant here and my manifold being compact, it doesn't matter what norm I fixed on the fibers of the tangent bundle, as long as it's, so that's what we mean by exponential. When I do these things in person, I sometimes do a version of dance that Maciej does, which is when you perturb in a stable direction, if you perturb infinitesimal in a stable direction, the new geodesic converges exponentially fast to the new geodesic. That's how you can think of it geometrically. But mathematically, it's nice to formulate in terms of differential. All right.
Right, thanks.
Questions?
Maybe we have time for another question. Yes, Laura.
So this seems to indicate that anywhere you perturb your hyperbolic metric, you're going to break the invariance by rotation by pi over 2. Do you think that's also true if you consider more general perturbation of the geodesic?
Yes. So the question is ultimately related to this theorem. So well, let me first answer, and then I'll give a remark about the question also. So here we consider conformal perturbations. As I said, we'll probably could have considered general metric perturbations. We'll probably give the same result with a bit longer computation. If you perturb the flow, so if you perturb it within the class of contact flows, it's always all contact manifolds that are nearby are just conformal to each other. There's no deformation there of contact structures, right? I forgot what's the name of that theorem, but anyway, so it's always going to be a conformal perturbation of the contact flow. And we actually have a theorem that if you perturb the contact form generically a little bit, then you will also have this answer. It's a simpler theorem to prove because you have more degree of freedom. You can use the result of Weiss that just shows that. Where is the thing? It's instead of showing that this push forward is non-zero, you just have to show that the form itself is non-zero, which is considerably easier. And in fact, you can show it has full support. But I should caution that we only do it for generic perturbations. So I anticipate that there is a finite codimension set of perturbations for which the degree of vanishing would be exactly the same as in the hyperbolic case.
Okay.
Just because if you think of a matrix depending with values, if you start with a matrix 0 and then you perturb it, so you have an m by m matrix and it has entries which depend holomorphically, even say, on some parameters. The dimension of the eigenspace at 0, well, it will be stratified, right? And for a generic small matrix, it will have no eigenvalue at 0, but there will be all this positive codimension strata where a lot of things can happen. And so in our situation, it's not going to get simpler than that. Yeah.
Okay. So
yeah, which is also why our conjecture here is really for generic metrics. Yeah. Which I think is probably the best you can realistically expect.
And does knowing the multiplicity of 0 have consequences on like asymptotics by some Tauberian means or something like that?
Asymptotics of sorry, I didn't hear you.
I don't know, geodesics counting or something like that?
No. So I gave a very short disclaimer somewhere near the beginning that we don't. So if you think about the singularities of the zeta functions, like, by analogy with the Riemann zeta function. So the first pole of the Riemann zeta function is at 1, and the only one. And that corresponds to the prime number theorem, right? And then if you want to push a little bit past this one, that's where the Riemann hypothesis, prime number theorem come in, and so on. But in our case, the first pole of this zeta function, or the first singularity, is not at zero actually. It's at the topological entropy of the flow. It corresponds, the corresponding currents, I think, correspond to Margulis measures, even though I'm not sure anybody has ever really figured out legally how to write microlocally. And so, and the topological entropy is some positive number. So it's pushing a bit past the topological entropy is where you get, this is what Juliet-Tillerani and Polikov, for example, were doing, where you get improvements in prime geodesic theorem. Our thing is all the way down to zero, which is very deep. But it's still kind of fascinating that it has to do with the topology.
Well, thank you very much.
Thank you, Laura, for the question. Do we have any other questions for Semyon? All right, well, thanks again, Semyon, for the talk today. We will reconvene next week with